So let's talk about countable and uncountable for just a minute. So countable, what does it mean for a set to be countable? S is countable if, and if and only if is a definition, countable, if there exists a function from S to N which is a bijection. How do I want to say this? Well, I would just write an extra arrow. It's bijection. Bijection, i.e., f of S1 equals f of S2 implies S1 equals S2. That's into. And for all integers, there exists an S with f of S is the same. So you hit every number. Nobody gets mapped to two different things. No two elements of S get mapped to the same thing. Okay. So why are the integers countable? So the natural numbers are countable because the function is the identity. Why are the integers countable? What's my map? Well, I just have to order them because I have an order on the natural numbers, so that's the function. So the order is 0, 1, -1, 2, -2, 3, -3, and so on. Why are the rationals countable? The rationals are countable. I have to order them, but they don't come naturally ordered like this by absolute value. I can order them by, so if I have P over Q, I can make a height function. Yeah, so the height of P over Q is absolute value of P plus the absolute value of Q, but let's just always think of rational numbers as having positive denominator and in lowest terms. So then for any fixed height, there's a finite number. So height equals 0. Well, there's no height equals 0, but there is height equals, so I can list the heights first. So height equals 1 implies P equals 0 and Q equals 1. And height equals 2 implies P equals plus or minus 1 and Q equals 1. And so on. So for each height, there's a finite number of possibilities. I can order the heights, and so each one has finitely many terms, and that's my ordering of the rationals. This is often done with like 0 over 1, 1 over 1, 2 over 1, 3 over 1, 0 over 2. I guess I don't need 0 more than once. 1 over 2, 2 over 2, 3 over 2. And if you have the same thing twice, you just kind of skip it. 1 over 3, and so on. 2 over 3, 3 over 3. You write this matrix, and then you do some kind of ziggy-zaggy thing through the matrix. But what that's doing effectively, every time you're moving along a diagonal, is you're moving along constant values of the height function. And then you catch the negatives in there somewhere. Okay? So that's why the rational numbers are countable, and just to cross all our I's and dot our T's, Y is R uncountable. Okay, so let's pretend that it is countable. In fact, the subset, not only is R uncountable, the subset of numbers whose decimal expansion between 0 and 1 only uses zeros and ones is already uncountable. So if you can't count these, you can't count the rationals. And why can't you count these? Well, let's say you had a way of ordering them. So the first one, so F inverse of 1, let's say is 0, 0, 0, 1, 1, 0, 1, 0, whatever. And F inverse of 2. In other words, this is the guy that gets sent to 1 under the map F that we discussed originally in the definition of countability. Here's our map F. Everybody has a pre-image, so it makes sense to say F inverse. So who's the first guy in the list? Who's the second guy in the list? Who's the third guy in the list? The first guy is this. The second guy is this. The third guy, f inverse of 3, is this, and so on. Okay, so assume we have such a function. The assumption is there is a way of doing this, bless you. There is an ordering. We make our ordering, and then I claim there's an element of this set S. This is our set S. So my claim is that there exists an S in S such that, well, I haven't constructed the function, such that there does not exist a natural number with f inverse of n equal to S. So I haven't made a bijection, right? And what is that natural number? The proof is, I'll just give it to you. S is equal to 0.1, 0, 1, and so on, where the 1 is not 0, and the 0 is not 1, and the 1 is not 0. So I'm changing in the nth entry. In the nth entry, I'm changing the nth. Well, in the nth decimal, flipping it from a 0 to a 1. Okay, so this is an element of S, because S has all the numbers that have zeros and ones. I flipped it, so it's not the inverse of 1, it's not the inverse of 2, it's not the inverse of 3, and so on. So the real numbers are uncountable. Yes?
Do you want to say, I mean, you could say this, but do you want to say something about this isn't another equivalent representation?
Yeah, I never liked this part of so people do this proof and they say, well, let's stick S in at the beginning. We can always do that. And then we find a new number.
I mean, like, you could have found a number in f inverse of n, but written in a different way in decimal expansion.
Well, that's exactly why I restrict it to zeros and ones, so that I don't have to deal with 0.99999 being equal to 1.
Right. So
yeah, exactly.
So this is just decimal expansions, so there's no question of carries, and any number in here is represented uniquely already.
Yeah,
Exactly.
that would just be a sentence in the proof.
That each number, any number in here, has a unique representation in this one.
Yeah.
Yes.
That's it.
Thank you. Okay. Good. Any questions on this? All right. I checked that off. Can we get back to where did we stop? Any questions from last time? All right. We got to get to the Cantor set because that is on your homework, and because it's great. So I'll talk about the Cantor set. Is there anything else I wanted to say? We got to interiors, we got to closures, we proved that the interior is open, we proved that the closure is closed. Did we talk about the boundary? I think that's where we, at least in my notes, that's where we stopped. So what is the boundary of a set E? The boundary of E. What's the boundary of a set?
Closure minus interior.
Closure take away
The interior.
yes, some people say closure take away the interior. Some people say closure take away the set itself. So if you're there, you don't count yourself. So the boundary of a closed set, for example, is the empty set.
Well, I guess because
For some people.
E closure is the union of E and the boundary, so you could say that, I guess.
Yeah, but union doesn't have to be disjoint union.
Oh, okay.
It's so I'll put an optional take away the interior depending on Stanch card should put E. I don't want to confuse you.
I don't think. Well,
Do they put it? I mean, that's what I
it
wrote
agrees
down.
on open sets. That's what it's
It agrees on open sets. Yeah, maybe you want closure, take away the interior. All right, and here's the definition I definitely need to get to. So E is perfect, which is horrible notation, because the word perfect means 10 different things, and never anything remotely relating to being good or, when you make a something, do not call it good. Give it a real name. Good is such a terrible name, and then great, and then wonderful compactification. Perfect, perfectoid, that I don't mind, because that at least has a ring to it. Perfectoid. A set is perfect. Okay, so what does it mean to be perfect? We talked about isolated points, did we not?
Yeah.
Yes.
No,
So it has no isolated points. has no isolated points.
I'll just say that.
Okay.
It's no isolated
Doesn't it have to be closed? That's all.
Your limit point if no.
Does it have to be closed?
You contain all your limit points.
You contain all your limit points. It has no isolated points. There's no, yeah, then it has no isolated points. It has,
Well, couldn't there be a
It could.
limit point outside the set with not isolated?
yeah, I think we're gonna say it's closed and perfect if a set is closed and perfect.
Okay.
Yeah, so Q intersect open interval 0, 1 has no isolated.
Has no
points,
isolated points.
It doesn't contain 0.
Yeah,
So it's not.
so it's not perfect.
Uh,
Do we want it to be?
oh, it is perfect.
Sorry, do we want it to be not perfect? I think, I'm just gonna say no isolated points. In closure, we can add or subtract as needed.
So it's really,
I thought,
really a closed set, it's really a closed set.
Because how can the open say 0, 1, be?
Sitting?
I think it's really, it's a closed.
You want me to say it's a closed set that has no isolated points? Again, definitions will change from book to book, and, you know, you can sort of look into any particular one. When they give you an exercise, they're thinking about something. There are all kinds of, I mean, yeah, maybe I should think a little bit more about, there are all kinds of places in Stein-Shikarchi where they say, here's a bunch of sets, they're disjoint. What they really mean is pairwise disjoint, which is, of course, different. And you're supposed to intuit that. So even that isn't perfect as a book, but yeah. Yeah, okay, we can call it closed.
What is the difference between disjoint and pairwise disjoint?
Oh, here are
Intersection.
3 rectangles which have no common intersection, but they're not pairwise disjoint. So for example, if I want to say that if I want to say, look, they're disjoint, and so the measure of their union is the sum of the measures, that would obviously not be the case. So what I mean is pairwise disjoint. So the word pairwise is sometimes. So I'm taking these definitions out of Stein-Shikarchi, and maybe I should be worrying more about other texts that use different standard
I think
notation.
Sancho uses E closure minus the interior. And
Interior?
Closed and perfect.
Okay, all right. I'll put the interior there. It's perfect if it's closed, and has no isolated.
Maybe root also does that.
Okay, good. Let's get to the Cantor set. So what is the middle thirds Cantor set, since you have other Cantor sets in your homework? The definition C is the Cantor set, is the standard Cantor set. So that's what we're going to define. So everybody, I shouldn't say everybody, not everybody has seen this. Get me started. It's going to be a subset of 0, 1. And, yes?
You iteratively constructed that's called C1, removing the middle
Great.
thirds.
So C1 will be, let's take out, we want it to be closed or open? Let's make this a choose your own adventure.
Remove the
Remove the open.
You better remove the open because you want the endpoints to be in there. So you'll remove 1/3 to 2/3. Okay, so C1 is the closed set 0 to 1/3, including 1/3, disjoint union 2/3 to 1. And then C2, so there's a nice way of illustrating this, which is you draw a circle for every interval you're taking out. So C2, we're going to take out that interval, and we're going to take out that interval. So that's C2. And then C3, you take out this middle, and that middle, and this middle, and that middle, and that becomes C3. And C4, 1, 2, 3, 4, 5, 6, 7, 8, and that's C4. Okay, and you keep going like this. So the intersection of all the CI is, by definition, this middle thirds Cantor set. And we should think of as if you're falling from the upper half plane, so here's the upper half plane. If you're falling from the upper half plane, if you manage to reach the ground, you landed in the Cantor set. Okay? Am I proving that it's perfect, or am I, so it's obviously bounded. It is closed. I think these are all exercises.
Yeah, perfect is an exercise.
Perfect is an exercise, good. It's closed and bounded and hence compact. It's totally disconnected. So
Also an exercise.
totally disconnected is another exercise. Disconnected. What does that mean, totally disconnected?
The only connected subspaces are the one, for instance.
Yes. Another way to say that is for all x not equal to y in the Cantor set, there exists, so let's say x bigger than y. Sorry, there exists a z not in the Cantor set, so that that slips in between. Good. And it's, as I said, it's compact and totally disconnected and perfect, and you will prove those in your homework. So, perfect. All right, let's get back to rectangles, exterior measure, and developing Lebesgue measure. Okay, so by a rectangle R, I mean a set of RD of the form A1, A1 B1 cross A1 BD in RD. Okay? That's a rectangle, so of course what I want, any notion of volume, which I'll write as that, whatever notion of this we're going to cook up, measure, it should be B1 minus A1 times BD minus AD. And we're going to try to use these to create our theory as a first step, and then we'll go back to abstract measure spaces. All right, so here's the definition. Union of rectangles, if R is a almost disjoint union of rectangles, if the interiors of the Ri are disjoint. So pairwise disjoint. This is where it's important to use words like pairwise. Ri, Rj. Okay, in other words, I want to be able to do this. I want to take a rectangle and I want to cut it up into rectangles. That's not a rectangle. There, that's a rectangle. Okay, so these are all rectangles. Rectangles by definition are closed and bounded. It's compact. Okay, so they're not disjoint because the edges overlap. But that's what I mean by a disjoint, an almost disjoint decomposition of a rectangle into rectangles. All right. So a set of rectangles is almost disjoint. Almost disjoint. This is what we're doing. Okay, so lemma, if I have an almost disjoint decomposition of a finite number of rectangles, if R is the almost disjoint decomposition of a finite number of rectangles, then the volume of R, or the length of R, is exactly equal to the sum of these rectangles. If I had an infinite number of rectangles, I could start getting into some trouble with how much overlap there is. Like we're taking away this finite amount of overlap. But if I had an uncountable number of rectangles, well, I could make little strips that are rectangles. Each one has area 0, has volume 0, and then I start adding up over all of them. And okay, so let's stick to finite numbers of rectangles. You see what I'm saying?
There's something in between them. What about count?
Right. Let's first think about, as you'll see, the proof very much uses the finiteness. Okay. So proof. Well, what am I going to do if I have one of these disjoint decompositions, and there's only finitely many? There's something very simple you can do.
Extend the line.
Extend all of them. So just make these cuts and that cut. Just make it a grid. Anytime you have a line that doesn't extend, make it extend. So it's just a grid. Proof. make it a grid. It's clear that you've subdivided these rectangles into further rectangles so that all of them are A minus B. Add them all up. You've added up this. It also adds up to the volume of this. Okay? So even if I have a countable, this proof won't work. If I have a countable number of rectangles, then I might have to cut it up too much in too many places. All right. Why am I talking about the measure of the Cantor set? I'm going to come back to the measure of the Cantor set. Yes, it is. Very good. But I want to prove that for you. Let me leave this here. Sorry?
No, it wasn't an exercise.
No, it's, all right, let's just do it, because it's, let's just do it.
Similar things for exercises for a fact.
So let's remember that the Cantor set, so let's call this a lemma. Whatever we want our notion of measure, again, to be, I guess I'm going to use this fact, although it's simpler than that. We want the measure of the Cantor set. Let me not use length, since that's we want whatever our notion of measure to be, we want the measure of the Cantor set to be 0. And the proof is very simple. Well, we certainly want, so the Cantor set, if you recall, is this intersection of the CJs. The CJs are unions of disjoint finite number of rectangles each. Okay? This is disjoint union of finite union of rectangles in R1. So they're just intervals, closed intervals. And each one, so let's look at what each of the CJs looks like. So again, let me draw the picture here. Here's 0 to 1. Each of the CJs is some number of intervals, and all the intervals have the same length. So how many intervals? Number of intervals in CJ.
2 to the k.
Right, each time, so the first time we made 2 intervals, the second time we made 4, the next time we made 8. So this is 2 to the j intervals.
Can you move the paper?
Minus 1.
So C1 had 2 intervals.
Right, okay.
And what is the length of each interval? So length of each rectangle. In CJ, the first rectangle had length a third, then a ninth, then a 27th,
To the j.
1 over 3 to the j. Okay? So the length of CJ of each CJ is equal to number of intervals times the length of each one, 2 to the j over 3 to the j, and that goes to 0. And C is the limit of these sets of finite rectangles. Good. That's why I put that there logically. Okay. In R1, there's an even better theorem. So in R1 only, we have the following theorem. Lemma theorem. Let's call it a theorem. You can describe open sets in a very clean way. Every open set in R is at most countable union of intervals, open intervals. Okay? So I don't know anything about O, except that it's open. Here's R1. Here's O. I don't know what it is. Looks like some stuff. But it's open. In fact, it is nothing but a bunch of intervals, possibly infinite intervals. Open intervals. Okay, let's prove this. So, if X is in O, well, it's open, so there exists an interval, X minus epsilon, X plus epsilon, which is completely contained in O. Let's call this epsilon 1 and epsilon 2. So there's some ball around it, but now I want to push the epsilon 1 back as far as I can and epsilon 2 up as far as I can. There exists an epsilon 1, which is a function of x, and an epsilon 2, which is a function of x, which are let's say, each one of these is the infimum, no, I guess I want supremum, over all epsilons. Let's talk about epsilon 2 for a second. You'll see what to do with epsilon 1. Over all epsilon, so that x to epsilon is a subset of O. Okay, so I have some point x. I know I'm in an open set. That means that tells me I have some ball. So, thank you, x plus epsilon. So that means I have some ball, I have some region. Now I want to push it out as far as I can. So here's my x plus epsilon 2 is here, and I do the same thing in the other direction, x minus epsilon 1. Okay, so there's these two functions which push out all the balls. All right, so trivially, hence, O, we've done this at every x, is a union over all x in O of these intervals. Let's call this interval I sub x. I sub x, where I sub x is x minus epsilon 1 of x to x plus epsilon 2 of x. And if one of these is infinite, that's okay. All right. I claim these sets are either completely overlapping or disjoint. So if this intersection is not empty, then I claim that in fact they're the same. And this is, I think, obvious. So if there's an interval about x, and it somehow intersects an interval about y, here's y, and there's some interval about y, here's iy, and here's ix. If they have some intersection, which, since they're both open, will be open, well, then it's clear I could have pushed y, then epsilon 1 of y isn't the smallest. I could have pushed it all the way out to here. And by the same token, I could have pushed epsilon 2 of x out there. So by maximality, by supremum of epsilon 1 of x, epsilon 2 of x, epsilon 1 of y, epsilon 2 of y, if they intersect, then they're equal. That's clear? Okay. So now these are intervals. So they contain rationals. Each interval contains a rational. Each interval contains a rational. And so...
And you remove the repeated ones?
Exactly. So we can write O. So I choose a rational at each of the intervals. There's countably many. So O is a disjoint union of a countable number, possibly infinitely, possibly countable, of these intervals. They're rationals. Okay? If you try to do this even in 2 dimensions, you're looking at open rectangles, and you can't even, once you put 2 open rectangles next to each other, you're in big trouble, because what do you do on this? You got to include that somehow, and you can't without making them overlap. Okay, so this is a very R1 theorem, one-dimensional theorem. Yes?
So with the rationals, you were saying that because they're countable, you can create a neighborhood around them. Is that what you're saying?
No, what I'm saying is each of these intervals is an interval, and being an interval in the real numbers means that there is some rational number here.
Sure.
So for each interval, I choose a rational number representative of it.
Okay.
But the rationals are countable.
Oh, I see. Okay.
That's why I wanted to prove that the rationals are countable, make sure that was there. So the rationals are countable, which means that this union of intervals is not an arbitrary union of intervals. It's an at worst countable union of intervals.
Maybe a silly question, but
Please.
it seems like you have this infinite set of intervals and you're choosing a rational for
I
every
have,
interval.
yes, yes.
Am I just being silly, or is that in any way related to axiom?
Well, you could, so certainly if I use the axiom of choice, then I can do that. Do I actually need to choose a rational? Or do I just say there are rationals in each one? Certainly it's enough to say there are rationals in each one. I don't need to know which one it is.
And they're disjoint.
And they're disjoint because the intervals are disjoint.
Okay. So you could use AC, but you don't.
I do not have to use AC, but because I'm going to be using, but we should use it only when we have to. We don't have to use it here. So-
What's the difference between saying there is a rational at each interval?
Yeah, how are you?
Yeah.
How are you trying to do
That's-
countable without like coming up with an injective map back to n that's gonna need AC?
Well, I'm just saying that there exists a rational,
Right.
and the set of all rationals is countable.
So,
I'm not saying give me one.
right, but you're saying the set of intervals is countable. So like there are countably many of these intervals, right?
Yes. I'm saying there can't be worse than countably many intervals. So each interval has rationals in it,
Yes.
and so to each interval, I can assign some number of rationals without telling you which one it is.
But to show this is countable, you need like an injective map. back
So I'm
to n.
choosing, here's the map.
Yeah.
You know, what's the famous saying? You don't need the axiom of choice on shoes, you only need them on socks. You know this?
No.
If you have an infinite collection of shoes,
Okay.
you can always choose the left one.
Sure.
If there's a map, you don't need axiom of choice. If you have an infinite collection of socks, you don't know which ones socks can go on either foot.
Okay.
And so then you don't have a robust way of choosing it.
Mm.
So here's what I'll do. I'll choose the set of all rationals in each interval
Okay.
to represent that interval. And that's the left shoe. And the set of all rationals is countable. Yes?
Couldn't you actually pick the rational by using your list of rationals and just say the first one on the left that's in the interval?
Since the rationals are countable, once I have one, what's the smallest one that's in the interval? That's a counting function. Or choose all of them. There's another hand.
I'm sorry, I was gonna ask before George said anything, if you use actual choice, doesn't that mean we can make this construction a disjoint union?
It is a disjoint union.
But not if we just say every rational. Right?
So let's not call it I centered at xi, but just I sub I. I don't need to choose the center to specify the interval. Good? All right. Very good. So that's just the one-dimensional discussion, just so you know, but we have to do, of course, much more than that. So on the real numbers, I mean, this is kind of very close to what Borel was doing when he made the original Borel measure on the real numbers, was using the structure of the open sets, and then you can just say, all right, I know what the measure of open sets is, and I'll create my sigma algebras out of open sets. We want to head towards a more general theory. So let me just note, for R, this is sufficient. Any open set you want to measure, all you have to do is measure an interval, because all open sets are anyway disjoint unions, countable unions of intervals. If you want to measure an open set, all you have to do is say, well, that open set is the disjoint union of some intervals, countable disjoint union of intervals, which will have measured the length of the interval. Okay? But we're going to do more general stuff. So let's get to exterior measure. Well, let me just show you what goes wrong. So what about RD? What about RD? So let's just try to do something similar. Okay, we can use balls, we can use rectangles or cubes. Well, we can have a description. Let's say you have an open set. You have an open set. Here's my open set in R2. So I can try to fill it with rectangles, maybe even closed rectangles. In fact, we're going to deal in a second with closed squares. So if I fill it up and I start asking, if I start filling this up with rectangles, as we're going to do in a second, and I say the measure of O is the sum of the lengths of these rectangles, or let's call them even cubes already. So these are QI, these are cubes. Just means I'm not dealing with 3 different side lengths or D different side lengths. All the side lengths are the same. I might want to say this. I might want to define that to be measured. Well, there's already a problem, which is let's do it even. I'm getting a little ahead of myself. The main issue with a construction like this is proving translation invariance. If I even slide this set over a little bit, now I have to make a new collection of cubes to tile it, And how do I know that there's any relation between the collection of cubes, the lengths of the collection of cubes I use there versus here? Of course, I can shift all the cubes over. But there are, if you want to say, but if you had come up with a different decomposition into cubes, how do I know that all the decompositions will be the same? Here it's the uniqueness of the expression of an open set as a disjoint union of open intervals that makes this completely airtight,
Yeah, well defined.
well defined. All right, so let's go into, let's develop this theory and make it airtight also. So the right notion to start with is exterior measure. So here's the notion of exterior measure, mu star. So this will be a measure on all subsets. So this is on all subsets of R, of RD, but it won't have the properties that we want unless the sets you're measuring are nice sets. So in the end, the true measure will just be the exterior measure, but we'll restrict the set of sets that we are allowed to work with. So for example, we can't use the Vitali set will be not a measurable set. The one we discussed on many lectures ago. Okay, so here's what we're going to do. So here's the exterior measure on any subset of RD. It's defined as follows. You take a decomposition, so write E, decompose E as disjoint, almost disjoint, cubes, Qj. Okay? And this will be countable, again, because the cubes contain rationals. So if you have a disjoint decomposition, by the way, finite, there's an exercise, I'm not sure I assigned it, that if you insist on finite decompositions of coverings, I just want coverings. I just want coverings. It's not sufficient. So you need countable. It's not sufficient to use a finite covering, and there's an exercise about that. So you look at a covering like this, and then an upper bound for the set E should be the sum of these. So we'll take the infimum of the sums of all of these lengths of cubes, which we can measure in the usual way, of all almost disjoint decompositions of U into cubes. Bless you. Okay, is it clear? So it's just what we said before. It's the outer measure. It's very close to what we'll want. Let's test this definition. Does it give some good properties? All right, test one. So this is maybe lemma. I mean, it's a trivial lemma. What about a point, a singleton? What's its measure?
0.
Why?
Because the infimum of the lengths goes to, you always get smaller and smaller because you'll never reach a point.
Yes, well, we could cover the singleton by the cube, which is, it's a closed cube, which has length x minus x. Okay, we're in RD, so I mean this is x1 through xd. Okay.
Epsilon is x minus epsilon at the intervals x minus epsilon and x plus epsilon, and epsilon goes to 0, and the intervals should be 0.
You if you want to, but we're using closed cubes,
So it does reach.
so it's already a closed cube. This set itself is a closed cube, and its length is this, and it's an infimum, and these are all positive, so 0 is easy. Here's something surprisingly not that easy. Here's a lemma. What is the actual, I should say m star. We're always dealing with exterior measure because we're not at measure yet. If you have a closed cube, so Q always means closed cube. Closed cube. If you have a closed cube, is its measure equal to its length?
It better be.
It better be. It better be. So certainly we have a cover of the closed cube by itself, and so proof. Because the closed cube does cover itself, you can't have a worse infimum, but in some pathological universe, maybe there's a covering that does better, that has a smaller infimum. Okay? So we need to prove the other direction. So we have our Q. Thank you. So we have our Q. This is our Q. And we have some decomposition into cubes. Countable decomposition into cubes is supposed to be equal length cubes, almost disjoint cubes, disjoint interiors, pairwise disjoint interiors. So let Q be covered by an almost disjoint decomposition of somebody. I need to know that this decomposition cannot have measure, let's see, that this infimum can't be less than the size of Q. So how do you prove that?
Assume it is.
Okay, we could try to do one by contradiction. Okay, so this is going to be exercise in epsilon of room. Make a little bit of room for yourself in a variety of ways. Yes?
Are you going to limit it to a finite union that
How?
has almost all of that covers almost all of it up to like epsilon over 2 and then?
If I don't cover all of it, then I have trouble saying what happens to the rest unless I somehow. I mean, there's a whole variety of ways that you could try to do this. But I want you to I want you to enjoy the fact that it's difficult to prove. It's not immediately obvious, given this definition, that the measure of a cube is the size of the cube.
Can you add epsilon to the exterior measure or something?
Well, we don't want to mess with the exterior measure, but there is a property of the cube that we haven't exploited to its fullest. It's related to what you wanted to say. It's bounded and it's
closed, so
and
it's compact.
how are we going to use compactness?
Finite sum. If
You
you cover by
have
infinite
finite
number,
number. Use open cubes to count that.
I want open cubes, but I have closed cubes.
Just, but yeah, so like, grow them a little.
Grow them a little bit.
by epsilon.
Grow them a little bit. Okay. For each j, there exists an open set Sj, open, which contains Qj. It's an open cube just a little bit bigger with the size of Sj, which is, again, it's just a cube, so there's no problem measuring this. Well, it's going to be bigger, but I don't want it to be much bigger. I want it to be only bigger by, at worst, epsilon over 2 to the j will be enough. Okay? So let's fix epsilon. For each j, you get this set Sj, which is open and covers the Qj and doesn't have too much more mass. Okay? The Sj's cover the Qj's, so the union, arbitrary union of the Sj's covers this almost disjoint union of the Qj's, which covers Q. And Q is compact. And Q is compact, which implies a finite number of the Sj's bounds it. Q is bounded by j going from 1 to n of some of these Sj's. And so the measure, so now we can bound everything. So, but the union, the finite union of the Sj's, yeah, I didn't even need this 2 to the j because I'm not taking an infinite sum. Epsilon is enough. So the union of the Sj's, what's the measure of this, or the length of this? This is a finite open set, so the length of this is at worst the sum of these guys, and each of these is at worst the length of the Q. Well, each of these is at worst the length of the Qj plus epsilon.
Or do we need it, because we don't know like what n is.
Yeah, let's do this. Here's a better way of doing it. Let's do 1 plus epsilon. Let's do a multiplicative factor of 1 plus epsilon. So then each of these is at worst Qj times 1 plus epsilon. And what we've shown, since this contains this contains Q. What we've shown is that this infimum is at least the size of Q times 1 plus epsilon. So the size of Q is a lower bound for 1 plus epsilon times this exterior measure. This here, so this is at least the size of Q. Can I separate this? Like that. This is a rectangle. This is a cube. It's covered by open sets. So the length of Q is at least the finite union of these open sets. The finite union is at most the sum of the finite sets, which is at most Q, the Q finite Qi times 1 plus epsilon. But of course, I can increase that to all the Qi. So this is all, let's put them all back in. And then, and now let's take in, so Q is bounded by 1 plus epsilon times this for any cover, which means it's true for the infimum cover. Or it's true in the infimum. There's no necessarily infimum cover. It's true in the infimum, which means it's true for M star. Question?
What is the vertical bars around the union of the SJs mean?
Right. I guess all I mean is this. So if I have a rectangle, Q is a rectangle, and it's covered by open SJs. Now I'm just talking about Euclidean lengths. I'm not talking about measures or anything that we have to define, just Euclidean lengths. The Euclidean length of Q is bounded below by the sum of the SJs. The volume of the Q's is bounded by the SJs because the finite union of the SJs covers Q.
So the lengths of the SJs, they're open cubes.
Yes. So it's still B minus A.
Still B minus.
Yeah, this I still mean, these are still open cubes. So I still mean B minus A in the length.
So I guess what's the proof of the first inequality? The length
This
of-
one here.
Yes.
So what do I mean to say? I just mean to say that Q is contained in these. Let's skip the first inequality and go straight to the second inequality. So Q is bounded by this sum.
Okay. So what's the proof of that?
What's the proof of this?
Yeah.
It's a finite collection. So if I have finitely many things that, I mean, does this need proof?
I think we can simply take the closed sets of, I mean, it's that like the closed sets of Fj, and then it is also a cover of Q. So by definition, it is.
I know like a union.
This was our, thank you. Thank you. I missed the key step. Thank you. This is Q, which is a rectangle. It's covered by, now let's add the closures, a finite union of closed rectangles. Our previous lemma, did I lose a page? Here we are. Our previous lemma about a rectangle I skipped the lemma.
No,
About that.
You said it today.
Well, no, I had another lemma that I wanted to say, which was that if R is contained in a union of rectangles, arbitrary union of rectangles, then its length is at most the sum of those lengths. And the argument is exactly the same. So you cut, so this argument, why did I want finiteness here? Because now I want to subdivide whatever these rectangles were that covered Q, I want to subdivide them into pieces that cover Q, and then just add the finite number of pieces. Okay, so this inequality is the argument on rectangles. We only have finitely many. Each one is at most the size of Q times 1 plus epsilon. Now I throw in all the other Q's just for free by positivity. This is the infimum. That's the argument. Okay, we happy with this? You want me to do it again? You're right. This is by rectangle lemma. rectangle.
lemma about open rectangles or closed?
Closed. So let's make this even worse by closing these guys. So I used their openness. I had to thicken it to get the epsilon, so that I would have open cover and use the compactness to find this finite subcover. Now make it even a little bigger by closing them up. Now I have a closed rectangle which is bounded by a finite length, finite union, finite collection of other closed rectangles. Now I subdivide those closed rectangles with our rectangle lemma, and now that gives me this inequality from which everything else is okay. Yeah, I must have skipped that because I had that lemma in my notes. This is what happens when I say, yes, this is all obvious, we'll all get it.
So could you just state the lemma one more time?
Yes. The statement of the lemma that I wanted, I'll put here, lemma, if R is contained in an arbitrary union of closed rectangles, not necessarily disjoint union of a finite number of rectangles, then the length of R is at most the sum of the lengths of the RJ. Okay? So this is the finite rectangle cover lemma or something. And that's exactly what I want to use in that argument. Question?
But what was the proof for that? Like, it's just like the intuition of like non-disjoint intersections and then.
Well, the non-disjointness only helps in the inequality. All we want is an upper bound. So you have a finite number of rectangles. Whatever they're doing, you chop them. Whatever x coordinates and y coordinates exist in your rectangles, chop it all the way across. Add them all up. They have to cover R, and that's just the lower bound. There could be more. There could be a lot of overlaps, but that just makes the whole sum bigger.
Like overlap is the reason for the lower boundness or the upper boundness.
Exactly. That it's a cover. So it's a cover. That means it covers all of R. So when you subdivide R into chunks, each chunk, since there's a finite list of these, each chunk is contained in some rectangle, and the length of R is the sum of all of the chunks of R. And each one is contained in some chunk of one of the RJs. Are we happy with this, or you want me to spell this out a little bit more detailed? The argument is just what I wrote here.
Just like that?
Yeah. Right? Except now it doesn't have to be an exact, it's not an equal sign here, it's just a cover. Great. Thank you. Thank you for keeping me honest. And once again making the point that look at how non-trivial it is to show that the measure of a cube is the length of the cube.
A closed cube.
A closed cube at that, yes. Good. The point is amply made, I hope. All right. How about an open cube? Let's work our way up in difficulty. Okay, so let me keep the definition of exterior measure here. So this is, what are we calling these? Lemmas? Lemma. Lemma. If Q0, how do I want to say this? If Q0 is an open cube, let me just call it O. O is equal to an open cube. So it's the interior of a closed cube. What page is this? 5. Okay? O is an open cube. It's the interior of a closed cube. So the claim is that the exterior measure of O is still the length of the closed cube. All right, now what?
Still get one inequality.
You still get one inequality for free. Yep. This is an infimum over all possible covers. So proof. One inequality is trivial. This way is easy. So Q covers O and is a closed cube. And hence mu star of O is at most Q, since that's an infimum. So it's the other direction that needs work. Proof in the other direction. How are we going to do this? So again, we have, let me draw the open cube as that. We need a closed, we take an arbitrary cover of closed cubes. How come we can't do better than Q as a lower bound? Okay, so let O be covered by a union of cubes, almost disjoint union of cubes, almost disjoint countable union of cubes. And now what? Yes?
So the almost disjoint countable union also covers a closed cube just a teeny bit inside of. Does that work?
Yeah, exactly. That's what we want to say. Because O is an open cube, so there exists, what should we call this? Q0, maybe? Q0 inside O, which is closed, which is a closed cube, with the length of Q0 being at least the size of O minus epsilon. Okay, so you have your open cube. I don't know how to draw an open cube. That's a soft open cube, and inside it is a hard closed cube. Q0 sitting inside O, without losing too much. Okay, now this is contained in O, and the Qj cover Q0. So the Qj, so O is covered by the union of the Qj. And so the infimum over all the Qj, which implies the infimum over all such, the infimum over all Qj covering Q0 has a sum which is at least the measure of Q0, which is the length of Q0. So this is using the closed lemma, the closed cube lemma. Is this clear? So I know that we've already proved that if you take the infimum of the Qj's that cover Q0, you can't do better than Q0. But Q0 has size at least O minus epsilon. Does that make sense? All right. Next. These things are I don't know about you, I find these things the hardest to prove. The things that are like, come on, this is obvious. That we defined it as cubes, but now we're taking open and closed sets and you gotta, what's that?
You have no tools.
You have no tools yet, right. All the tools from your intuition are challenged. Once you build up these baby steps, then you can start using tools. Then you can, okay, I know I can cover this by open cubes or closed cubes, whatever it is that we want to do. All right. Here's something that's easy from the definition, or basically immediate by definition of, so note, this isn't even a lemma, this is just by definition of what infimum is. Can you still see the infimum of E up there? I want you to see that, and I want you to see the note, and there's no good way of doing it, so I'm going to do that maybe. Note, if E is a subset of Rd, is arbitrary, then for all epsilon, there exists a closed cube cover. There exists a cover by closed cubes, countable, such that the sum of the lengths of the Qi is at most the measure of the E's plus epsilon. That's just what infimum means. I can get arbitrarily close. Infimum means I can make this as small as I want, and so the fact that this is an infimum means for any positive epsilon, if I make it a little bit bigger, then I can find a closed cover that does it. Okay, so that immediately gives us, so now I can, okay, we're happy with the definition of exterior measure. You take this cover and you take the infimum. That gives us an easy corollary, a corollary of a note. Maybe I can't make it a lemma, there's no proof. The proof is the definition. The corollary is monotonicity. Monotonicity, which says that if E1, arbitrary subsets, E1 is a subset of E2, then the measure, exterior measure of E1 is at most the exterior measure of E2. Why?
Every cover of E2 equals.
Any cover of E2 is a cover of E1, right? And now use the note. Okay. Proof any cover of E2 covers E1, and then use the note.
Could you move up?
So far, so good. All right. Here's another corollary. If E is bounded, then it has finite measure. How do you prove that?
It's big enough.
It's contained in a cube. Proof E is contained in some sufficiently large enough cube.
And then use monotonicity.
With plus monotonicity and the size of a cube being finite. Okay. Let's prove countable sub-additivity. This is good, important. Countable sub-additivity. Now we're getting somewhere. Okay, so if E is equal to the union of EJ, arbitrary, so even this exterior measure will be able to prove something as interesting as countable sub-additivity, then we have countable sub-additivity. Countable, we have a countable cover. EJ covers E, not open, closed, just arbitrary sets. Then the exterior measure of E, sub-additivity, it's bounded by the sum of the exterior measures. Let's prove this. Okay, if the measure of E is infinite, then there is nothing to prove. What do you want to do? Yeah?
Do you want to intersect with a big enough square or cube?
What do you mean?
Oh, sorry.
If its measure is not if it's bounded. Just
Yeah, yeah.
assume its measure is
I get.
finite.
I don't know if this is useful, but I'm saying if its measure is finite, then outside of certain, if you go out far enough, it has small measure out there. So you
Okay.
could consider it within a box and outside the box.
Okay.
I don't know if that's what you want.
We don't need to do that. I don't see how that helps. It's an interesting idea. What? Well, these aren't even open. These are. We're not assuming anything about it. It's just
like E is contained in the union of the first n sets for all n?
E is Q, and then
E is contained in the union of the first n.
Yeah, that might not be written down.
Yeah. Why does it have to be? This could be just. This is totally arbitrary. All I know about it is countable.
Yeah.
That's going to be important. We're going to use countable. There's a reason I went over the proof that Q is countable. It's, I guess, a hint.
For each EI, there exists a cover,
Yes.
so that sigma
Yes.
Q.
If we want to prove this upper bound, it suffices to prove it for any possible cover. Okay? So if, so let's say let each EJ be covered by some, how do I want to do this? A disjoint union or almost disjoint union. Let's just say it doesn't even, we don't really, since these are upper bounds, we're not worried about the disjoint or not disjointedness. I need a new letter. K goes from 1 to infinity of Q, J, K. Can I say that? So each one of them is bounded by this countable set. So let E be bounded like this, And here's where I want to use this note. I can find one. So can find such with the sum of the q, j, k being at worst the measure of e, j plus. Now we want the epsilon over 2 to the k, 2 to the j. Does everybody see that? So we take our EJ, we cover it by cubes. Each one we're going to cover by cubes, so that this cube cover is no bigger than the full whatever the infimum is, plus an epsilon over 2 to the j. So let's fix epsilon, which will be arbitrary. Okay, again, we're giving ourselves an epsilon of room. So that's this cover, but then qj, the union over, not disjoint, the arbitrary union over j and k of these q, j, k, it covers the union of the ej, and the union of the ej covers, in fact, it's equal to e itself. So this is a countable collection of cubes. Countable of countable is countable. That's cube. Monotonicity, the measure of E is at most the, well, no, I can't use monotonicity because this is a countable set. I don't want to use that. I want to use what I just proved here. The sum of all of these, so let's sum this, let's sum both sides of this. This is sum over k. Now let's sum this over j. Summed over j, summed over j, and summed over j. E is covered by these rectangles. And so mu star of E is at worst, because I've exhibited one such cover, and mu star by definition is the infimum over all possible covers. Here's one such cover. It's the sum of the j and the k of the lengths of q, j, k, which is at worst the sum of mu star e, j plus epsilon. Okay? So finite subadditivity is very important fact, and it's already true for the exterior measure. All right. Sorry, did I say finite I mean countable subadditivity. We have time for a question? No. We have time for a couple more. Let's do a couple more. What other properties? We're building up our intuition of this notion of exterior measure. What other properties of it do we want to say? Great, here's another lemma. Here's another potentially useful lemma. If it is useful. Let E be arbitrary. Arbitrary. So E usually means arbitrary set, O usually means open set, Q usually means cube, R usually means rectangle. Then the exterior measure is in fact equal to the infimum over all open covers.
Can you scroll it down a little bit?
Sorry.
Is
Is that better?
Yeah, it's better.
Of the measures of the open covers. So we didn't have to use cubes in the end. We could have used open covers. Or now, from now on, if it's more convenient to use open covers, we can. All right, let's prove this.
Excuse me, let E in RD be
Arbitrary.
uh,
Arbitrary. Can you read that?
Thank you.
You just can't read that corner? Let me write this better. Then the measure of E is equal to the infimum over all open covers of, what am I saying here? The sum of the, let's say, the sum of, question?
Is this saying something different than if you just said it's equal to the infimum over E contained
I'm
in a
sorry,
single
I'm sorry,
open
I'm
set?
sorry. I don't mean covers. I mean just open cover.
Just contained.
Just contained in an open set.
Yeah.
It's the infimum
Oh, okay.
over all open sets.
But it says it's, does it say the same thing?
Well, because accountable, because an arbitrary union of opens is open. Yeah, so what I mean is, should I write this again? Let's write it again. Lemma. If E is a subset of RD is arbitrary, then its measure is equal to the infimum over all open sets containing it of the measure of that one open set. It's not something about countable unions. Let's prove this. Again, one direction is trivial. E is contained in O implies we proved monotonicity already for arbitrary sets. So we need to prove the opposite direction. Okay. As usual, we're going to, what are you going to do? Yeah, let's add epsilons and move things around. So what's a slick way of doing this? So for the other direction, we need the other direction. So let's say E is covered by O. And let's take an open cover for E, because I want to prove the inequality in the other direction. So take a cube cover, take E contained in a bunch of cubes.
I don't think we need to say O up front, right? We construct O by the cubes. That,
Okay, yeah, in other words, we'll construct an O.
yeah.
Yes, thank you very much. We will construct an O. We want E to be contained in an O. With this inequality, of course, we need some epsilon. Okay, so that's where we're headed. Take E subset of O. We can get through this. We can do this. These are closed cubes. E is contained in this. With the property, again, by what this symbol means, with the property that the sum of the M star of the Qi being bounded by the measure of E plus, let's call it epsilon over 2. There'll be a couple of epsilons floating around. Okay, this is again just by infimum, by the definition of M star. Okay, for each j, Qj is a closed cube. That's not good. We want an open cover. So there exists a open cube containing Qj. Let's call this Oj.
And then epsilon over 2.
With the size of Oj at most the size of Qj plus, yeah, I guess epsilon over 2 to the j and plus 1 just to give me another factor of 2. And now we're done. Then the union of the Oj is open. It covers the Qj and hence covers E. And now let's look at all these lengths. So these lengths are also the measures. We saw that the measure of an open set is its length. So this is equal to the measure of Oj, and this is equal to the exterior measure of Qj. And so now let's sum on J, sum on J, sum on j, and this is no longer an equal sign, plus epsilon over 2. Countable additivity says that the the OJ, well, they make some open set. Let's call the union of the OJs the set O. So the measure of the set O, which is the union of the OJs, by countable additivity, is at worst the sum of the J's of the mu star J's, which is at most the sum of the QJs plus epsilon over 2, which is at most the measure of E plus epsilon over 2. And 2 epsilon over 2's make an epsilon. Did everybody follow that? Should I do it a little slower? There's some confused faces.
Where did the second epsilon over 2 come from?
Okay, so if I take this inequality, this is because I made the OJs a little bit bigger than the QJs,
Right.
but only this much bigger. So now sum on the J's.
Okay.
So the sum on the J's gives me a sum over the mu star OJs. The length of the OJ is the same as mu star, that we proved.
Right.
The length of the QJs is the measure of the QJs.
Right.
And then the sum on J, because there's an extra factor of a half, is an epsilon over 2. Okay. Now we're using countable additivity to say that the measure of O is just the union of these OJs,
Right.
open, is at most the sum of these. So that gets us this inequality. This inequality was summing this term by term. Now, the QJs were assumed to be a cover of E, whose sum of measures is at worst the measure of EJ plus epsilon over 2.
Yeah, okay.
So that's the last step. I stick it in here. I get an epsilon over 2 and another epsilon over 2. This is true for every epsilon, so we get our inequality in the other direction.